Good afternoon, and welcome to the first physics colloquium of the spring semester. So I just wanted to take a moment for those of you who I haven't met, since I'm new here. So I'm Nevin Weinberg, one of the new faculty members. The other new faculty member is Rick Wilder, who with me will be organizing the colloquium this semester. So you'll probably be seeing me or him introduce some of this semester's speakers. I also just wanted to point out that for technical reasons, the live event format wasn't working, which is the format we were using the previous semester. And so instead, this is just a regular Teams meeting, which basically just means that you want to make sure your mic is on mute. You can unmute yourself, but you shouldn't, at least not until the Q&A session at the end of the talk. So if you have questions during the talk, please just type them into the chat the way we've been doing before, and I can relay those to our speaker. And yeah, as I said, at the end of the talk, we should have time for a Q&A, and I think then we can sort of use the unmute buttons to directly talk with the speaker. So with that, I'd like to introduce our speaker, Professor Ian Crossfield from Kansas University. So Professor Crossfield did his PhD work at UCLA. He was then a postdoctoral fellow at the University of Arizona and UC Santa Cruz. And from 2017 to 2019, he was an assistant professor in the physics department at MIT. In January 2020, so basically exactly a year ago, he moved to Kansas University, where he is now an assistant professor in the Department of Physics and Astronomy. So Professor Crossfield's research interests include exoplanet formation, detection, and characterization, and also the development of instrumentation to further those pursuits. So he makes extensive use of both photometry and high-resolution spectroscopy from both the ground and space, and he's also the lead of the Exolab at KU, which is dedicated to discovery and characterization of nearby planetary systems. So in addition to the NASA Sagan Fellowship, he was awarded the Doxy Prize of the AAS and was a Kavli Frontiers of Science Fellow. And so today he's going to be telling us about the discovery and characterization of sub-Neptune exoplanets. So Ian, whenever you're ready, you can unmute your mic and share your screen.
Okay, great. Thanks a bunch, Nevin. And to all of you there for giving me the chance to talk today and for bearing with me in my first 24 hours of using Microsoft Teams. So it seems to be going okay so far. Maybe someone can confirm that you can hear me or see me?
Yes, we see you and we can see your slides. Yeah.
Great. Okay, so again, it's a real treat to be here today. It's an honor and a privilege to give the Inauguration Day colloquium at UTA. Not everyone gets the chance to do this, so I appreciate it. And I'm excited to have the chance over the next hour or so to talk to you about the work that I and my group have been doing, finding, and even more than finding, characterizing and sort of getting a more detailed sense of the nature of extrasolar planets, planets around other stars. And just a reminder again, as this setup works, I can't see if you're typing questions in the chat, but Nevin or Rick, if those questions come in, don't feel you have to wait until the end of the talk to ask them. So feel free to keep those questions coming during the talk. All right. So because, this will be an astronomy-focused talk. I know a lot of you aren't astronomers, so I'll try to walk us through things. But if there are things that are confusing, please just let me know. So let's go ahead and get started. So first of all, it's an exciting time to be studying exoplanets. It was just a little over a year ago, that actually the field of exoplanets was validated in the eyes of our physicist colleagues by winning a Nobel Prize based on sort of the real kickstarting of this field back in 1995. And so highlighted here are Michel Mayor and Didier Queloz, who discovered the first exoplanet orbiting a solar-type star. And of course, two of the last three Nobel Prize years have gone to things relating to black holes, but it was nice to see exoplanets finally get that prize as well. So we were all happy about that. In other ways, too, it's an exciting time because this field is really expanding and exploding, and it's been a really sort of meteoric rise over the last 25 years or so since that first first recognized exoplanet was really discovered. So just to set the stage a little bit, this is a common type of plot that we exoplanet astronomers like to show. And you've got, maybe someone can confirm that you can see my cursor, just to make sure.
Yep, we see it, Ian.
Great. Okay, so you've got here in the x-axis the length of a planet's year in days. And right, based on Kepler's laws, that's equivalent to plotting here the orbital separation of a planet from its star. You can interchange between those two. And here I've got on the vertical axis the size of a planet. And if we plot some of the known planets in our solar system on this plot, it makes my choice of limits for these axes seem a little funny. We've got our inner Mercury, Venus, Earth, Mars. Jupiter fits on, and Saturn, Uranus, and Neptune are just off the side of the plot. They don't even show up. So the reason I choose these particular limits is this is actually basically all the parameter space that we know of for known planets around other stars. And if I plot those, here's the Nobel Prize-winning planet, and you can see this is a real oddball compared to the planets in our solar system. It's substantially bigger than Earth, Venus, Mars, or Mercury, about half the size of Jupiter, but it's way close into its star compared to all of these. Mercury goes around the sun in about 90 days or so, but the 51 Peg B, the name of this planet, it goes around its star every 4 days. So it's just a few hundredths of an astronomical unit from its star. It's like 1,000 Kelvin, so very hot place. It was a very unusual planet and a surprising discovery in a lot of ways. If you had asked astronomers, I think 25 or 30 years ago, what are most planetary systems like, we didn't know any better, and so I think we would probably have told you they were more or less like the solar system. And there are some that are like the solar system, but we now know that there are many more that are not. And so in the years since, we've found thousands of these planets. This is just a subset of them. And you can see that they almost occupy a disjoint space relative to the known planets in our solar system. There's really only one or two planets known in the sort of size, year parameter space near, say, Earth or Venus. There's a few more near Jupiter, but nothing near Mars or Mercury. And you'd be correct if you guessed maybe that was at least partly due to selection effects. So part of what we do as astronomers, as exoplanet researchers, it's not quite that we're doing fundamental physics, right? We're not probing the fundamental building blocks of the universe, for example. It's more akin to we can just go and observe what the universe is like and try to explain and understand why it is the way we see it to be. So sort of the universe is our observational laboratory, but the experiment has already been set up and started running, and there's nothing we can really do to change it one way or another. But I think the physics equivalent would sort of be that we're either theoreticians, or in my case, we'd be sort of an experimental physicist. But you can just call me an observer too. So it's not quite that we're trying to identify a standard model of planetary systems, right? That would be sort of an ideal goal and sort of a nice analog to physics studies. But in practice, we're really trying to we don't hope to do so much. We don't think that there's sort of a single narrow model that explains all this diversity, but we can still hope to learn some trends and figure out what's underlying it all. There's a couple different populations and trends and actually absences of things that show up here. So shown up here, this hot Jupiter population, this is sort of typical of the vague sort of names we've given these classes of planets. These are things that are really hot because they have very short years, and so they're very close to their star, and they're roughly the size of Jupiter. So hot Jupiter. This was the first sort of exoplanets to be discovered, not necessarily because they're very common, but just because it's really easy to find something that's very big and that's orbiting very close to its star. It's very easy to find those. On the other hand, it's much harder to find things that are smaller or that are on longer period orbits. Another feature that's popped up is actually an absence of planets and that's this sort of what we call a hot Neptune desert. And it's more sort of a wedge-shaped part of parameter space. But there are few, if any, planets that are known in this region that are sort of intermediate in size between the Earth and Jupiter, and that are on very short period orbits. But there are hot Jupiters on short period orbits like that, and there are actually small rocky planets on those short orbits. So this is one interesting dearth of systems. Another population that's emerged is these cold gas giants. So these are things more or less like Jupiter. So they're dominated by hydrogen and helium, their bulk composition, but they're on much wider, longer period orbits, sort of 1 astronomical unit or further out. And so I said it's easier to find things to the top left of this plot and harder to find them to the bottom right. Well, these hot Jupiters, although they seem overrepresented in this diagram, intrinsically, they're actually quite rare. It's just that it's so easy to find them that for many years they were being discovered by the dozens, and few, if any, other types of planets were found. And you have to observe a system for many years, potentially, before you can identify for sure that it has a cold gas giant. So it's tougher to find these systems. Also tougher to find are these smaller planets, which sort of go by various names of sub-Neptunes, things sort of smaller than Neptune, or super-Earths, which are bigger than Earth. We do sort of think there's a distinction between these two, which I'll come to in a minute, but they're both sort of a size of planet of which we have no examples in our solar system. So they're interesting in that way too. And they seem to be much more common than these sort of intermediate-sized Neptune planets. Because they're smaller, they're tougher to find, but we see more of them. So there must be a lot more of them. And then finally, some of the most interesting parameter space, one of the big questions in the field of exoplanets is how many Earth-like planets are there, or how frequently do those occur, however you define Earth-like to be. And to date, most of those Earth-sized planets on an Earth-like orbit, they're mostly undetectable around other stars. We have very little sensitivity, not quite zero, but it's very tough to say. We don't think, for example, that every star has an Earth-sized planet in an Earth-like orbit. But we don't think it's zero either, but it's somewhere in the middle, unfortunately. We'd like to know that a little more precisely than we do. So that sort of just sets the stage of some of these different populations of planets and where we're going. So these planets are discovered and initially characterized through different observational techniques. And it's fun to find them, but if you're just interested in finding planets and not doing anything with them, you're sort of just stamp collecting. And so we want to do something scientifically useful with them as well. I think there's a couple different productive avenues of research once you've found some planets. This is probably not an exhaustive list. One of these, you can characterize these individual planetary systems in great detail. You can measure the planet's orbit, its mass, its radius, its density, maybe its orbital eccentricity, other parameters of this sort. Sort of full system characterization. And maybe that'll tell you something about how planets initially form, how do they migrate, topics like that. Another thing, which is something I'll talk a lot about in this presentation, is you can try to characterize their atmospheres. You can learn through remote sensing techniques what the atmosphere might actually be made of. Is it mostly hydrogen and helium? Is it something else? Is there interesting chemistry going on? How does the atmosphere circulate in the planet? Are there jet streams or vortices or what have you? So you can try to do that as well. And then another big area that I won't talk so much about is that we can try to infer planetary demographics. And that also tells us about formation and migration and what are the typical types of planets that might be formed in the galaxy and in the universe. I'll mainly focus on these first 2 points. So one of the ways, probably the most productive way we find these planets is shown by this little animation here, which is called the transit method. A planet passes in front of its star and blocks a little bit of the brightness of that star. And so we see the star's brightness dip a little bit as the planet goes across. And then once the planet has moved away, then we see the star return to its original brightness. And if this repeats periodically, you can infer that there's a planet orbiting the star periodically. And from the depth of that dip, how fainter the star gets, you can also measure that with space telescopes like Kepler here in the upper right, or TESS here in the upper left, both NASA space telescopes. And the depth of this transit, as we call it, is actually directly proportional to the cross-sectional area of the planet to the star. So astronomers have studied stars for over a century, so we have a pretty good handle on how to estimate the size of a star from other means. And so if you can do that and find a transit and measure its depth, you can directly infer how big the planet is. And that's where most of those planet sizes on that diagram I was showing earlier come from, these sort of measurements, transits. A complementary technique that's been probably the second most productive is what's called the Doppler shift technique, or radial velocities. And the idea is, sorry if that's flickering a bit oddly, if a planet is orbiting around a star, they're really both orbiting their common, just to show that again, they're both orbiting around their common center of gravity. And anyway, and if the star is also undergoing a smaller orbital modulation, the stellar velocity imprints a Doppler shift on the stellar spectrum, and we can actually observe that from ground-based observatories, and we can infer a planet is there as well. And that gives us the mass of a planet. So if a transit, shown here on the vertical axis, gives you a radius of a planet, and this Doppler shift technique gives you the mass of a planet, then you can measure both and learn the density. And that tells you something about the bulk composition of what the planet might be made of. So you can plop down some sort of models on this sort of graph. So these are just sort of notional toy models that are sort of limiting cases. For a given mass of solid iron or solid silicate or solid water, not solid, but pure 100% water, you can say how big would that planet have to be. It shouldn't surprise you that 20 Earth masses of iron is going to be a lot smaller than 20 Earth masses of water. Iron is more dense. So, like I said, these are just toy models, limiting cases. But those are just, you can make more realistic models as well. But you can also start plopping down your observations of what these different systems actually look like. And so all of these measured, these points with their error bars show individual measurements of different planetary systems. This is from a paper by my graduate student, Molly Kosharek, from a couple of years ago now. And you can see that there's sort of a whole continuum of planetary properties. There's no narrow main sequence. There's no clear narrow trend of planetary properties here. We can generally see that maybe at the lowest mass planets, maybe many of these are all smallish. Maybe they're all roughly consistent with some sort of rock, silicate, water mix. But at the larger masses, they're even more diverse. There are massive things that look like they could conceivably be made of pure iron, though I don't think anyone would tell you they think that's actually the case. There's probably something else going on there. But there's a whole large number of planets that are up above this 100% H2O line. And so those are all things that we call gas giants or ice giants, like our own Uranus and Neptune in the solar system. This U and this N are where Uranus and Neptune would be. They have to have something even less dense than water to make up most of their composition, and we think that's hydrogen and helium. So these are some of those sub-Neptunes, and I would say those super Earths I talked about more are these things that are more dominated by rocks and denser materials, whereas the sub-Neptunes are sort of analogous to our own Neptune. So maybe I'll just let's see. One more point is just that one thing we've discovered just in the last couple of years is that these super Earths and sub-Neptunes seem to occur with roughly equal frequency. So this histogram now is showing versus the size of the planet, how many planets there are per star with shortish orbital periods, because that's where we have the most sensitivity. But still, what we found, thanks to the Kepler mission, is that there's this large peak of sort of 2.5-ish Earth radii planets. And these are what I think we would call the sub-Neptunes. They have to have a substantial amount of hydrogen and helium to puff them up to that size. And then there's a real shortage of intermediate-sized planets, and then it's sort of 1.5 or so times the size of the Earth. These are what I would call the super-Earths. They're presumably mostly rocky, and they probably, I would say it's fair to say, they probably form in a fundamentally different mechanism than these puffier, more rarefied sub-Neptunes. And this sort of histogram lightly continues here down to Earth sizes, but there's no error bars plotted, and it's all pretty light-colored. As I told you, those occurrence rates are pretty poorly known still, so the error bars would be much larger. And finally, just a final point, these larger planets 10 times the size of the Earth, like Jupiter, are intrinsically very rare, even though they're easy to find, and I looked on that plot, like there are lots of them. It's easy to find. So I'll pause a moment and ask our moderators just to see if there have been any questions so far on any of these points.
No, none have shown up on the chat. Hopefully the chat is working, but I don't see any yet.
All right. Yeah, I hope mute all doesn't also mute everyone's keyboards. Okay. As I said, if you do have questions about any of this, feel free to type it in the chat anytime. So we can measure the mass and the radius of a planet, as I said, and that gives us a rough handle on, is there probably a lot of solids or is there a lot of gas? But it doesn't tell us much more than that. So the next step in characterization of these things, in terms of the work I do, is to try to figure out what the planet's atmosphere might be made of in a more detailed sense. Of course, I'd be interested to know what its solid interior is made up of as well, but most of these planets, the atmosphere is the only part we can see. Just like in the solar system, if you take a telescope or binoculars and you go and look at Jupiter or Saturn, like if you caught that great conjunction a month or so ago, all you're seeing is the atmosphere of the planet, well, and you see Saturn's rings too. It takes a lot more work to tease out anything going on beneath the cloud tops.
Ian, we have a question in the chat.
Great.
So why is enstatite so prevalent?
Why is enstatite so prevalent? I'm not saying that any of these planets necessarily are made of enstatite specifically, just that it's a common mineral found in rocks here on Earth, and there are therefore models of sort of planetary composition versus mass versus radius for models with that sort of composition. I wouldn't, like I said, these are sort of limiting cases, and I wouldn't take it to say that this planet here is mostly water, or even that this planet is mostly iron, or the planets in the middle are mostly terrestrial-like rocks. It's more informative than just having the measurement points and no point of mental comparison.
So we have one more question, if
please.
Okay, so is there any possible way to confirm if the exoplanet has internal magnetic fields or not?
Interesting question. There are studies that are underway to try to measure the magnetic fields of exoplanets. I think in the near term, the only hope for doing that is really, well, you can hope for technosignatures from some alien civilization, but that's a totally topic for another talk. The bigger hope, I think, is for interactions, but either interactions between a planet and its moon, like Io and Jupiter in our solar system, or between a close-in orbiting planet and the star itself in kind of an analogous configuration. So people are making those sort of studies. If you were talking about a planet like the Earth, they're tough enough to find, let alone to characterize. So magnetic fields on those are, I think, many years off. All right. So like I was saying, the sort of next step is to try to characterize the planet's atmosphere. And one of the main ways that we do that is through something called transmission spectroscopy, or transit spectroscopy. And it's a way we probe the atmospheric makeup of these exoplanets. So it basically relies on the transit method, which I talked about a little already. A blue planet here passes in front of a red star, and the apparent flux we measure from the star drops a little bit for a while the planet's in front of it, and then the flux goes back to normal. The key to transmission spectroscopy is we can make this measurement at multiple wavelengths. Lambda is what we use for wavelength. So if you measure at lambda 1, the transit depth that you see, if the planet has an atmosphere, and you measure the transit at multiple wavelengths, at some other wavelength, lambda 2, you might actually measure a deeper or a shallower transit. And the reason for that is that atmosphere, it's made of any kind of material at all. It absorbs light more preferentially at some wavelengths, and it transmits it preferentially at other wavelengths. Like our own Earth's atmosphere is very transparent at visible light, but it's moderately opaque at many infrared wavelengths, or in the ultraviolet below the ozone cutoff, the Rayleigh scattering cutoff. So if you make many measurements of transit depth as a function of wavelength, you can build up what we call a transmission spectrum, or a transit spectrum. And it's basically just a measure of transit depth here on the vertical axis versus wavelength. That's all it is. And so if you do that, you can then compare your measurements to models of atmospheric composition and behavior, and you can try to infer what the atmosphere might be made of. There are some degeneracies, but you can make a lot of headway. So this shows a sort of example transmission spectrum. Unfortunately, not of an exoplanet. This is actually a transmission spectrum of Saturn's moon, Titan. You can see a picture of Titan over here. Titan is this hazy covered moon with a surprisingly dense atmosphere of nitrogen and other species. But you can measure a transmission spectrum of it analogously as we do for an exoplanet, but at higher singleton levels. And you can see here these strong absorption features, which are higher measurements here. For example, the atmosphere absorbs light preferentially at wavelengths where we know methane, CH4, has strong absorption bands. So it's good because we've sent probes to the surface of Titan. We know there's methane in its atmosphere. Similarly, there's another big methane feature here, another hydrocarbon feature. Some hints of other species, like this bump down here is generally coincident with where we think carbon monoxide has its fundamental row vibrational absorption band, maybe some other hydrocarbons. So you can make a good model, you can match the observations. In this case, it just confirms what we knew about having sent things to Titan as well. But for exoplanets, remote sensing is the only thing we can do in the time scale of one graduate student thesis. So we have to make these sort of measurements for exoplanets. We do that with various telescopes. The ones I'll talk about here are mainly ones that have used measurements from the Hubble Space Telescope, or HST. And these are the transmission spectrum of 6 sub-Neptunes. Twiddle here, because it depends on how you define it in terms of mass or radius. But I'd say these are all sub-Neptunes. And so this is a figure from a paper that Laura Kreidberg and I wrote a few years ago now to try to understand what explains this diversity of transmission spectrum. So some of these exoplanets show pretty clear, largish amplitude features relative to the noise. Some of them, like this blue one here, seem to be perfectly flat, showing no spectral features at all. And others, like this yellow one here, sort of seem to show some interesting linear trend. And so for any of these, we'd like to know, is this telling us something real about the planets? If so, what is it telling us? Is any or all of this relating to some sort of systematic or observational errors? And how can we work toward a sort of closer to getting a first principle sort of understanding of what's dictating the atmospheric properties of these planets? And when we did this study just a few years ago, I said the field of exoplanets has been going for over 25 years now, but it's really only in the last couple of years that any sub-Neptunes have had good atmospheric measurements. And so you can see the dates of these individual individual studies were initially published. And this is a couple years ago now, but when we wrote the paper, it was only about 3 years ago that the earliest of these had been put out. So, whereas this has been done for those hot Jupiters for 10 or 15 years already. So, we set out to try to explain this diversity. So, the way we did that was, the main feature here in these spectra is a feature of water vapor absorption. We're not resolving individual lines in the spectrum. This is just an averaged, very low spectral resolution absorption band of water vapor. If your eyes could see at 1.4 microns of light rather than at optical wavelengths, you wouldn't be able to see much, even on a clear day, because the Earth's atmosphere, specifically the water vapor in it, absorbs pretty strongly at that wavelength. Similarly, it does in the atmospheres of these exoplanets. So we were really just empirically measuring the amplitude of that absorption feature in each of these spectra. You'll notice that the ones that showed those features all seem to have similar looking spectra, similar shape. So what we found was that it seemed like the most likely culprit for explaining this trend that we were, for explaining these measurements that we saw, was a correlation between the equilibrium temperature of the planet and the amplitude of that water vapor absorption signal. So that blue spectrum I pointed out that was very flat, basically zero amplitude, well, that's actually the coolest planet in our small sample. And the purple and the light blue one that showed the largest amplitude signals, those are actually the warmest Neptunes in our sample. So it's not every point fits on the trend. Of course, by general statistics, you should only expect 2/3 of your points to match within the error bars. So we sort of meet that criterion. And it's a small sample, but it at least seems to explain the data. So it was a possible trend. The question is, why should the temperature of a planet relate to the amplitude of its spectral features? And there's sort of two main ways that could be explained. Either these weaker transmission spectroscopy features either indicate intrinsically lower water vapor abundance, or some sort of high-altitude clouds or hazes, some sort of aerosol in the atmosphere that blocks light equally at all wavelengths, a gray absorber, and that prevents us from seeing whatever interesting molecules are actually in the planet's atmosphere. So it could be either of these in principle. However, there's no real reason to think that the chemical abundances of a planet and its atmosphere should tightly correlate with the planet's temperature, with how much it's irradiated. We don't actually think that all of these planets formed where we see them today, so it would be a little odd if there's a tight correlation between the chemical abundances and the temperature. Plus, these Neptune-mass planets are actually predicted to have higher heavy element fractions than the bigger Jupiter-sized planets. This is a plot from a simulation of sort of population synthesis model trying sort of first principles to predict what types of planets would form around various types of stars and what those planets might be made of. And so for various assumptions, they actually found that some of the highest heavy element mass fractions in the planet's atmospheres were found around sort of 5 to 30 Earth masses, right in that Neptune mass range, compared to those larger, heavier planets that are mostly hydrogen and helium, so very few heavy elements of any kind. So we think that this lower abundance explanation probably doesn't hold water. And probably what we're seeing instead is that these cooler planets, for some reason, their spectra are more preferential to, are more likely to be blocked and obscured by some sort of high altitude aerosol, whether it's clouds or hazes of some sort. And there's actually some theoretical motivation for this. It's not totally just a just so story. So this is some modeling done by Carolyn Morley, one of your UT colleagues, I guess at the other UTA over in Austin. and she did some work simulating how much haze should be in the atmosphere of one of these Neptune-like planets relative to how heavily the planet is irradiated. Which correlates to what's the temperature of the planet. And so she found that for these less intensely irradiated planets that are sort of 400, 600, 800 Kelvin, that there was increasing amounts of haze material, sort of photochemical hazes, sort of smog that forms from photochemistry of the planet's atmosphere. There's a lot of this for these coolish temperatures. But that there was a really sharp cliff somewhere between 800 and 1100 Kelvin, call it 900 or 1000 Kelvin, where suddenly these hotter planets might be much more haze-free. There might be almost none of this photochemical smog in their atmosphere at all. The atmosphere would be clear, conceivably, and so therefore that might explain why the cooler planets have a lot of haze, so we see only weak or no spectral features, and maybe the hotter ones we see the full spectral range because there's few, if any, chemical hazes to block those transmission spectra. So maybe all of these cooler planets are covered by some, or maybe even sort of Titan-like atmospheric haze. Because that transition, that cutoff, that cliff at around 900 Kelvin, is predicted by more of these simulations, is right around at the same temperature where we saw sort of that distinguished our higher spectroscopic signal planets from the cooler ones. So Laura Kreidberg and I had modeled this with a linear trend. But with this sample, you actually imagine you could fit this with a step function, and it would be about as good of a fit as a linear trend would be. But either way, it sort of seems to hang together that maybe these cooler planets are covered in hazes, the hotter ones might be clear, and so maybe that explains this diversity that we see.
So Ian, we have a question in the chat asking about what do you mean by heavy elements? Is that just nuclei heavier than helium?
Thank you. Good question. That's right. Sorry, I should have mentioned that we astronomers play pretty fast and loose sometimes with our elements. We know that there are a lot of them, but we really just like to often consider that there's hydrogen in the universe, there's helium in the universe, and then there's everything else. So when I said heavy elements in that simulation a few slides ago, that was just anything heavier than hydrogen and helium. It's a good question. And I should say, there's every reason to think that these planets have very complicated chemistry, but because the only spectral feature that this data from the Hubble telescope is really sensitive to is water, H2O, we already understand there's probably hydrogen because we know how puffy these planets are. So really all we're talking about here is the oxygen content of the planet's atmosphere. So we're not saying anything necessarily about any of the other heavy elements. But it's the only best observational probe that we have for these planets, so we have to move forward with what we've got. Good question. All right. So the issue, of course, is that maybe we were just making a mountain out of a molehill. We really need a bigger sample. No robust theory was ever proved, I think, by six data points, some of them with really whopping uncertainties that didn't fit your model anyway. So we pointed this out very clearly in our paper and said we needed a bigger sample to show whether this trend really exists or is just a statistical fluke. You'd need both hands and toes, I think, to count all of both hands and feet, to count all of the supposed trends in exoplanets that haven't actually stood the test of time. So we knew that. So what I and my group have done have spent the last couple of years trying to address that issue, trying to go out there and build a bigger sample of these measurements. And so just last year, my graduate student, Sherry Guo, who's shown here, who's since defended, she made another set of these same sort of measurements for the sub-Neptune HD 97658b. If you haven't seen yet, many of these planets just sort of have telephone numbers instead of names. So this was a planet that was actually on our trend here before, but we were able to get additional data. So Sherry combined the new measurements we had and reanalyzed the old data. And it turned out, we were very pleased to find, that this spectral modulation that you see in the data from her paper, the amplitude of that places this right on this trend line. So that was very surprising but heartening, actually. When we went out and made some other measurements as well. So this is Dr. Tom Evans, who's a postdoc who's been working with me. He just recently put out a paper on planet HD 3167c. And you can see the measurements here compared to a couple different models comparing the planet's spectrum. And again, the amplitude of the spectral features, sort of the peak to valley, if you want to eyeball it, corresponds to this black point over here on this figure. So it's not quite on that trend, but it's not so far off it either. So that's not too bad. My collaborator Laura Kreidberg also had a paper making similar measurements on the warmer Neptune 106315c, and that point plopped that planet right on this original trend line that we had predicted. So it seemed like, overall, more planets than not were coming in, at least not inconsistent with our trend. And there have been a number of other measurements by a few other groups that have expanded this as well. And so this is now the new full population of sub-Neptunes. This is from a paper we've got in preparation. And it seems like the trend that we identified is still holding. And so we've got these hotter planets whose atmospheres are mostly clear. And it looks to me like they're mostly clear around 850 Kelvin or so. There aren't too many of these Neptunes that are substantially hotter, although there are hot Jupiters that go hotter, but we understand that's a different beast, a different type of planet. These Neptunes, these sub-Neptunes, over this range of temperatures, error bars are big. Of course, we'd like them to be smaller, and we'd like more measurements on the line, but they seem to roughly follow this trend. And then there's some sort of cutoff temperature, and below maybe 550 to 600 Kelvin, there's a couple planets here that show no spectral features at all. And at least one interpretation of these is that they're fully hazy. There's just like those models from Morley that I was showing, so much photochemical smog is being produced in these atmospheres that we can't actually see deep enough down through the haze to see the water vapor that we're interested in. So instead we see no spectral features. And then there's also this really weird oddball called K218b, which actually shows very strong water vapor absorption, even stronger than these hot Neptunes. So this is a temperature that wasn't actually explored by those earlier models of Morley. So there's active work in progress to understand, should those photochemical hazes, should they drop off again? It seems to be what's predicted by this one planet, but it's only a sample size of one, these low temperatures. So we still need more data, of course. But this original trend of clearing hazes at higher temperatures seems to hold. And this is just sort of what I was saying before. It seems like these aerosols just gradually turn on, I would say, as the temperature decreases from 1100 Kelvin or so down to cooler temperatures. I would say there's this linear trend is the simplest model you can use. I think you could also, like if you wanted a two-part stepwise function, you could have one set of hazes for these hottest planets, an intermediate haze level for all of these intermediate temperature planets, and then maybe totally hazy for the coolest ones. But it doesn't quite work, but there could be other models. Anyway, it seems possible at least that these aerosols are very opaque, and then they totally clear for these coolest temperatures. This is an ad hoc model. What we'd like is to be able to compare this to real microphysical models of haze and cloud formation in planetary atmospheres to understand, if not from first principles, at least from second principles, why we're seeing what we're seeing. So there's been some work on that front, because we'd like to explain this emerging atmospheric sequence of these sub-Neptune atmospheres. These are sort of color-coded by their temperature, And it really does seem like they get flatter and flatter for the most part toward cooler temperatures until you get to this weird K218. We'd like to explain that. We've identified it empirically. Now we'd like to know the physical mechanism. And I think this is a very promising avenue for work. So my work is more in the observational sense. But other folks like Peter Gao over on the West Coast, who has been doing some of this microphysical aerosol modeling. He was focusing on hot Jupiters, but he had a paper come out just about a year ago predicting the amplitude of water vapor features as a function of equilibrium temperature, the same axes we've been looking at here. But he was doing it for hot Jupiters. He wasn't really considering the Neptunes because the hot Jupiter sample size is a lot bigger. What he found is these clear sky aerosol-free models, or these tracks up here that really only match one of these hot Jupiters. And all the rest of the population is really better matched with his models they're very aerosol-rich. There's lots of atmospheric haze forming in these models. So it seems like for the hot Jupiters, haze is very clearly the preferred explanation. It's interesting. We can actually zoom in on the sub-Neptune regime down here in the lower left and actually see how these models of his compare to those Neptune measurements I've been plotting as well. And actually, it turns out they match pretty well. So if we zoom in a little bit, these points with error bars are the same ones I've been showing you before. Now this is the Neptune population, again, not the hot Jupiters anymore. But this purple region is sort of region of predicted spectral amplitude from these first principles microphysical haze formation models of Gao et al. And they seem to perfectly explain all of the warmer Neptunes over the range of temperatures that he considered in his models. He cut them off at about 700 Kelvin because he was focusing on the hot Jupiters. And so we're now actively working on exploring what these same sort of models predict for the cooler part of the Neptune population. I think it's going to be that we're finding something that more or less matches our empirical fit. But we'd like to actually have that matched by physical models as well. So I think that's right. That's about all I want to say on transmission spectra. And honestly, I think I'd rather just, in the interest of being fair to everyone, let's just head to the conclusions here and leave it there. And if there really aren't any questions, I can opine on a few other things. But otherwise, I think I'm happy to leave it here, that we've been rapidly expanding this sample of sub-Neptunes with atmospheric measurements, specifically with the Hubble Space Telescope. There's an even sort of the successor to Hubble is something called the James Webb Space Telescope, which is expected to launch this October, and that's going to do an even better job than Hubble has done at understanding these planets' atmospheres. It'll really shrink the error bars on all of those points. There seems to be this pretty clear trend that has withstood the test of time of aerosol prevalence in planet atmospheres with temperature. Temperature as parameterized by irradiation from the star, really. I talked mostly about photochemical hazes. I think there are ways that this could be condensate clouds formed by condensation, like water clouds in Earth's atmosphere, but different chemical species here. But it's not quite as likely. And anyway, it seems like these warmer planets, by virtue of having these bigger, stronger spectral features, are probably going to be, the warmer ones will be the ones that are easier to study. And these cooler ones are going to be just tougher to study because those hazes are blocking things. I just skipped to keep everything sane in terms of the length of this talk. I didn't really talk much about this ultra-hot Neptune that we've looked at. And certainly you should look for many more surprises once we actually start looking at these things with the James Webb Space Telescope. Every time we have new observational capabilities, we're surprised. And there's every reason to think that that'll continue with James Webb as well. So with that, I'm happy to take more questions, and thank you again for the chance to talk to you all.
Great. Thank you very much, Ian. That was a very nice talk. So there was a question a little bit back in the chat. When we measure the radius of the planet using transit data, we should also consider the inclination angle. How can we measure inclination?
That's a good question. So, to the extent that stars and planets are spheres, which is a pretty good approximation, not perfect, the inclination angle of the orbit doesn't matter. The transit depth will be the same if it transits exactly across the middle of the star. It'll be the same depth as if it transits a little bit off the equator of the star in either direction. In sort of higher order considerations, it can matter sometimes for various reasons. But luckily, we can measure that by the... let's see if I can stop sharing my screen. You can still see me, I take it?
Yep, I see.
So, if you've got your star here, and a little planet is crossing in front of it and transiting, you see flux versus time in the planet's atmosphere. And so if the planet goes right across the equator, you'll see a pretty sharp-edged transit. But if the planet goes, because the planet has some finite size, so if it instead is transiting near the edge of the star, then actually the transit duration is a little bit shorter. And the shape of this ingress, we call ingress and egress, will be a little bit different. So instead, you'll see something that looks like, starts a little later, and it hardly has any flat bottom, and it looks something different.
The edge of your board is cutting off on the screen, or at least on my screen. Yep, perfect.
Thanks. Yeah. So anyway, the point is, from the shape of that transit, I only talked about the depth of the transit in my talk, but from the other details about the shape of it, we can actually also infer the inclination. Is it perfectly edge on? Is it tilted a little bit? Of course, if the planet, just to switch back to make sure you can see it, if the planet were a little bit, if the orbit were a little more inclined, it would never actually pass in front of the disk of the star, and then we just never see it transit at all. Maybe you could find it from that Doppler technique, but maybe not. Anyway, that's probably more than the question the master was wanting to know about inclination.
Okay, great. Let's see. So we have another question. So UA, I see you have a question. Would you like to just unmute and ask it, or if you prefer, I can ask it for you?
Oh yeah, sure. Yeah, I can see that. It seems like haze block the observational capability, and I was wondering, how different is the composition from haze on one exoplanet to haze on another? And in the future, is it possible we can, generate some instrument based on new technology to penetrate the haze and make observation, below it?
Great question. Yeah. So there's a saying, right, that every challenge is really just an opportunity in disguise. And so this one is no different. There's many people who are actively hoping with this new James Webb Space Telescope I mentioned, because it will cover a much broader range of wavelengths that Hubble is able to access. And so with many wavelengths comes greater diagnostic power. And so we think that we should be able to discriminate somewhat between different haze compositions, like if it's some sort of condensed mineral clouds versus some sort of photochemical hydrocarbon haze. Maybe also say something about the distribution, the number size distribution of what these particle sizes typically are. So I think there is some observational hope with that, with facilities that are coming on soon. At present, we don't know much about the haze composition. We know that it's there in many planets, but we can't say much more than that yet.
Thank you.
So we have another question from Manfred. Did you want to ask it? I am muting.
Well, I can ask, yes. Of course, it was very interesting listening to your talk, and in the end you jumped to the conclusions, and you, yes, mentioned the James Webb Telescope. So my question is, can you a little bit elaborate on the potential of the James Webb Telescope regarding your envisioned research?
Sure, good question. So the main advantages of James Webb are, I guess I'd say there are three big advantages over anything we have right now. The first I just mentioned, which is the expanded wavelength coverage. So most of the most strongly absorbing molecules in these planets' atmospheres, molecules, right, have most of their absorption features in the infrared. And so James Webb is optimized for the infrared in a way that Hubble isn't, and it goes further into the infrared than Hubble does. So we're going to have access to many more molecular diagnostics than we have with our current facilities. The second, I'd say, is that James Webb is a bigger telescope than Hubble, and so if we're ultimately limited by Poisson noise, and so the more photons you collect, the higher your precision on your final measurement. So it'll help that way too. And I think the third way is that James Webb, although originally envisioned as a cosmology machine, a lot of smart people have spent a lot of time over the last decade or so figuring about how to fine-tune it and optimize it for exoplanet science in a way that the Hubble instruments were never envisioned to make these sort of measurements at all. So we're always pushing them beyond their design capabilities.
Thank you.
You're welcome. We're excited about James Webb.
So I had a question. If it's haze and clouds, I would imagine it's going to be time dependent in some way. So if you went back and revisited some of these planets that you already have data for, would you expect the spectrum to look somewhat different?
That might be one of the $64,000 questions in the field. There's been a lot of work about people trying to find evidence of planetary variability. The trouble is, the size of the error bars that I was plotting there. So for those sort of measurements, for those transmission measurements, you're really integrating over the entire circular limb of the planet. So you need strong variations to make the integrated average of all those variations be something that shows up, because there's a lot of different atmospheric patches that you're averaging over. So probably the variability signal is subtle, and I think any plausible variability signature, the tools we have so far just aren't sensitive to it.
But these are mostly circular orbits too. Like I can imagine if it was a very eccentric orbit, then you have a time-dependent temperature.
Sure, that's true. So there are planets on these sort of plunging eccentric orbits that they spend 80 days far from the star, and then they spend 2 hours, a hundredth of an AU away from it. They sort of get flash heated by the star. And so there have been some successful measurements, I guess, even with existing observatories, measuring, for example, what's the time constant? How long does it take the planet to heat up due to this heating? And so that does tell you things about the timeliness of the response of the planet's atmosphere to some processes. I was just thinking sort of day-to-day variability, like today it's cloudy, but yesterday it was sunny. But yeah, I think probably the quickest and most productive path to learning something about variability is studying those sort of eccentric planets.
Great. So let's see. So we're just past the hour now, and I don't see any more questions in the chat. So with that, I'd like to thank you again for the talk and the visit today. We really appreciate it.